Hello, chemists. This is Miss Placino, and you are watching Screencast 12.4 on calculating pH. Today's lesson is really all about calculating the pH of strong acids, weak acids, and of bases. You're going to want to have a calculator for today's lesson, more specifically one that has the log function. All right, let's talk a little bit about the pH scale, which is hopefully familiar to people from either middle school or some other earlier science class. pH is just a way of expressing the concentration of H plus ions. Don't forget, we can also call those H3O plus or hydronium ions in an aqueous solution. We use everything, or I guess I should say we compare everything to 7. A pH of 7 is neutral. If the pH is less than 7, that substance is acidic. If the pH is greater than 7, that means that solution is basic. So here we've got just a picture of one. Again, water right at the middle at a pH of 7. We'll talk about why 7 is used as our neutral number a little bit later this lesson. And as the numbers increase, you get to materials that are more and more basic. If you look around your house, a lot of your cleaning supplies do tend to be basic in nature. Things like ammonia are found in Windex, window cleaners. Bleach is not on this picture, but bleach is very basic as well. If we head in the opposite direction and we go lower than 7, we see things becoming more and more acidic. A lot of your foods tend to be a little bit acidic in nature. And of course, over at the very low end, at about a pH of 0, we see strong acids at relatively high concentrations. Common misconception about pH has to do with that somehow pH is indicative of the strength of an acid or a base. Hydrochloric acid, for example, is listed as the most acidic substance on this scale. Hydrochloric acid at a concentration of 1 molar will have a pH equal to 0, but it is possible to take vinegar. The active ingredient is acetic acid, and get a really high concentration of vinegar and see extremely low pHs. On the opposite side, I could have a very dilute solution of hydrochloric acid that could have a pH pretty close to 7, still on the acidic side of 7, but pretty neutral nonetheless. Same thing applies to bases. Just because you see a very high pH, a pH close to 14, that does not mean that we have a strong base necessarily. That's just telling us that the concentration of H plus ions in that solution is very, very low. So it's really important to break this common misconception. pH is not telling you the strength of an acid or base. We know that that's all about extent of dissociation, covered in an earlier lesson. pH is just looking at the concentration of H plus ions. What we're really focusing on today is calculating pH, and this is a formula you won't find on your reference table. So pH is equal to negative log of H plus ions. The pH scale is logarithmic. This is a pretty easy formula to use. For most people, it's just kind of figuring out when you punch in the formula onto your computer, do you punch log and then the concentration of H plus ions, or, H plus ions and then press log. So you're going to have to figure it out. Everybody's calculator is a little bit different. pH is used because it's going to enable us to express the concentration of hydrogen ions in a way that's a little bit easier for people to think about. Every time you see a 1 unit change in pH, you've got a 10 times concentration change of H3O plus ions. So trying to explain to somebody that the concentration of H plus ions in solution is 1 times 10 to the negative third molar, that really doesn't make sense to most people. If you tell them it has a pH of 3, all of a sudden that makes a lot more sense. People know, oh, it's acidic, but it's not, unbelievably acidic. So this is why we use pH. So if we have a solution that has a pH of 3 and another one that has a pH of 6, hopefully we know that the pH of 3 has a greater concentration of H plus ions than the pH of 6. For acidic solutions, the lower and lower you go, the more H plus ions in solution. So as far as calculating the concentration, or how many more times concentrated the pH of 3 is, that's a 3 unit change, so I'd say 10 times 10 times 10. Or the solution with a pH of 3 is 1,000 times more concentrated in terms of H plus ions than the solution with a pH of 6. A really common mistake is to take the number of units change, in this case 3, and multiply that by 10 and come up with 30 times more concentrated. Don't do that. That is not how this works. You have to multiply them. So again, every 1 unit change in pH corresponds to a 10 times concentration change of H plus or H3O plus ions. So let's go ahead and try this out. Let's say that we have a 0.025 molar solution of HCl. First thing we need to do is find the concentration of H plus ions. HCl is a strong acid. Hydrochloric acid dissociates completely, so if we have one HCl molecule in solution, it's going to break apart into one H plus and one Cl minus. With strong acids, it's really easy to figure out the concentration of H plus ions, again, because they dissociate completely. The concentration of the acid itself is going to be equal to the concentration of the H plus ion, as well as our anion, but usually we don't really care about this when we're studying. We're trying to figure out pH. I know my formula. It's pH is equal to negative log H plus. I'd really encourage you to write your formula. Just get in the habit. You know, I look for this on things like quizzes and tests. Plug in your number. pH is equal to negative log 0.025 molar. And you come up with a pH of about 1.6. And that's all there is to it. The tricky part is always getting to the H plus ion concentration, which should hopefully be pretty straightforward with strong acids. So we've got these three practice problems. What I'd like you to do is write a dissociation equation for them. I'd like you to figure out the concentration of H plus ions and then finally come up with the pH of this solution. So pause the video and try these out. So I've gone through and written my dissociation equations. Hopefully they're pretty straightforward. Acids always lose one H plus ion at a time, and all of these acids are monoprotic, meaning they just have one hydrogen that they can donate. So check and make sure you've got the same dissociation equations. As we talked about on the previous slide, the concentration of H plus for a strong acid is pretty easy to come up with. It's going to be the same as the concentration of the original acid. Finally, we're going to plug into that formula. Negative log of the H plus ions is going to be equal to pH. So you can check your math. For question number 1 with nitric acid, you end up with very low pH of 0.42. Remember, there are no units for pH. For our perchloric acid, we got a pH of 3.4. And finally, for our hydrobromic acid, we got a pH of 7.2. So 1 and 2 make a whole lot of sense. We've got acidic solutions when we see pH is lower than 7. However, on this last question with hydrobromic acid, we've added an acid or a substance that's capable of releasing H plus ions into solution, and somehow we've ended up with a basic pH. Ooh. Even though this is a really dilute concentration or dilute solution of hydrobromic acid, there's no reason that adding an acid should make the pH turn basic. So if you came up with 7.2, your calculator's right. That's how you do the math. But from a sanity perspective, this makes absolutely no sense. You shouldn't see a basic pH for an acidic solution, regardless of how dilute it is. So there's something else that we have to take into consideration when we're working with acids, and actually bases for that matter too, we'll talk more in a minute, at very, very low concentrations. And that is the self-ionization of water. Water actually is a very, very, very weak electrolyte. That means that to a small extent, water is able to break apart, or we got in this picture, we have two water molecules kind of reacting together to form H3O plus and OH minus. So even if you're working with just pure water, you are going to have some, very, very few, but not zero, ions in solution. And at about 25 degrees Celsius, we know that the concentration of hydronium ions and the concentration of hydroxide ions will be equal to one another, and that concentration is 1.0 times 10 to the negative 7th molar. If you take this number and you plug it into the pH formula, you end up with a pH equal to 7. So the pH scale being based around 7 was not chosen arbitrarily. It has to do with the concentration of H plus ions in pure water at 25 degrees Celsius. So this is where it comes from. To get back to our other issue with our acidic solution somehow having a basic pH, we need to take into consideration the fact that these H3O plus ions from water exist in solution as well. technically they're always there, and you could go through and add them in for every single acid that you're working with. Most of the time, if you're working with a reasonably concentrated solution of acid, there's really no point in going through this extra step. But since we're working with a very, very dilute solution, it does make a difference. So when you've got exponents of -6, -7, -8, -9, so on and so forth, you really need to add in water. And let's talk about how to do that. So with our dilute solutions of acids, we've got to take into consideration that water, to a very small extent, ionizes. So I know the concentration of my acid, so I know the H plus concentration due to the acid. I also know that I've got water present. It doesn't matter how much water is there, you always end up with this 1 × 10 to the -7th molar concentration of H plus ions from water. We're going to add those together. You get 1.64 × 10 to the -7th molar. Let's plug that into our pH formula, and you get different results. Now the pH is equal to 6.8-ish, which, it's still very close to 7, but at least it's on the correct side of the scale. Again, there's no reason that adding an acid like hydrobromic acid should ever cause the solution to turn basic. So just be careful with this. Make sure that you're not just rushing through things and you're just happy that you have an answer on your calculator. Check and make sure it makes sense. Acids have to be below 7. Bases, as we'll see in just a minute, have to be above. All right, moving on. Let's talk about pOH. This is probably something you might not have heard of. pH is much, much more common than pOH, but pOH is just a way to express the concentration of hydroxide ions in an aqueous solution. It's used far less frequently than pH, and we're just going to use it as a means of calculating pH. There's a relationship between the pH and pOH of a solution. If you take those two and you add them up, you get to 14 every single time, regardless of how concentrated the H plus or OH minus ions are. This relationship is always going to hold true. So what we're going to do, if we're talking about a base, it's easiest to calculate pOH because we know we can figure out the concentration of hydroxide ions pretty readily. Then we can plug back into this formula, basically take 14 minus pOH, and we can calculate the pH of that solution. So let's work on some practice problems. All right, so let's say that we have a 0.5 molar solution of sodium hydroxide. Just like with the with the acids, go through and write your dissociation equation. It can sometimes be a little bit trickier with bases because they will dissociate all of their hydroxides at a time. Not so much an issue with sodium hydroxide as it's just a 1-to-1 ratio between our cation and our anion. Sodium hydroxide is a strong base, so if we have 0.5 molar solution of sodium hydroxide, we'll have 0.5 molar concentrations of sodium and of hydroxide. Just like last time, we're going to ignore our spectator ion. In this case, we're just really interested in the OH minus. So the first thing that you want to do when you're finding the pH of a base is to calculate pOH. It's calculated the exact same way as pH, except of course we're going to look at hydroxide ion concentration and not hydrogen ion concentration. So I plug in, I come up with a pOH of 0.3. To calculate that the pH of this solution, I can use this relationship. pH plus pOH equals 14. I know the pOH is 0.3, so 14 minus 0.3 is going to give me 13.7 as a pH. Now you're familiar with the pH scale. We know the pHs of bases need to be greater than 7. This is fairly concentrated at 0.5 molar, so it makes sense that we've got a high pH. So calculating the pH of a base is a little bit more work. You've got this additional step thrown in there, and you have to calculate pOH first, and then you can get to pH using this relationship. So let's try a couple of practice problems. All right, so what I'd like to see for this set of practice problems, tell me the hydroxide ion concentration. Let's figure out the pOH, and then ultimately we'll get to the pH. So pause the video and see if you can figure out those 3 pieces of information for these 3 practice problems. Let's take a look at these three problems. So question number one, I've got a 0.045 molar solution of calcium hydroxide. So the first thing I asked you to calculate was the hydroxide ion concentration. Calcium hydroxide is going to produce 2 hydroxide ions every time it dissociates. So that means my OH minus concentration is 0.09 molar. And I plug that into the POH formula. I come up with a POH of 1. And I know that POH plus pH equals 14, so that means the pH of this solution is roughly 13, depending upon how far out after the decimal point you went. If we look at rubidium hydroxide, just a single OH minus ion, so concentration of the hydroxide is equal to concentration of the base. Plug in, you get a POH of 2.1, and therefore a pH of 11.9. And careful with question 3. We've got a really dilute solution of potassium hydroxide. Just like with the last question in the acids practice problems, you have to add in this case, the hydroxide ion that comes from water. So it's always adding the same number, 1 times 10 to the negative 7th molar. So this has a pretty substantial impact on the concentration of hydroxide ions. I end up with a POH of 6.99 and a pH of 7.01. So be careful. Bases can be a little bit tricky. If you've got multiple hydroxide ions, you need to make sure that you are reflecting that in the hydroxide ion concentration. And when you're working with really dilute solutions of bases, same thing applies as with acids. You have to add in the hydroxide ion concentration from water. So a little bit more work. You have to find POH before you can get to pH, but it is still very manageable. All right, the last type of problems that we're going to really try to tackle are weak acids and pH. So if we remember weak acids do not dissociate completely. Instead of just seeing the forward reaction only into H plus, but whatever the anion is, we've got a reversible reaction. So this is nitrous acid, which is a weak acid. So if I start off with a 2 molar solution of HNO2, since this is reversible and we're going to establish equilibrium, I have to go through a little bit more work to figure out the concentration of my H plus ions. And actually, I think I'm going to open this up in a different program so it's a little bit easier for you to follow along. So give me just a second. Let's do that. All right, I'm going to look in here. So the first thing you should do is write your dissociation equation. We've got HNO2, reversible reaction with the hydrogen and the nitrite ions. We know what the Ka is, and in a previous lesson we talked about how to find the H plus ion concentration of a weak acid. You can go through and set up a Rice table, but at this point in time in chemistry, we know that everything is going to follow the general format of Ka is equal to the concentration of the reactants, of the products over the concentration of the reactants. And we're always going to end up with Ka, in this case 4.0 times 10 to the negative 4th, is equal to x squared over just the concentration of the acid. Generally, X is so small that when you subtract it from the concentration of the acid, it doesn't really make an appreciable difference. So this saves us a lot of headache, namely the quadratic equation, by just simplifying it to this. So when you go through and you solve for the concentration of hydrogen ions, in other words, you solve for X, you should come up with 0.028 molar. Now that we know the H plus ion concentration, we're going to calculate pH the same way we have all lesson. We know that pH is equal to the negative log of the H plus ions. So pH is equal to negative log 0.028 molar. The pH of this solution should be then about 2.4. Right. So again, when you're working with a weak acid, you have more work to do. You cannot just look at the concentration of the acid and immediately jump to the concentration of the H plus ion, you've got to set up this acid equilibrium constant, and we talked about it. It always is really going to condense down to this. Ka is equal to x squared over the concentration of the acid. Once you know the hydrogen ion concentration, you kind of just go about your business the way you did when you were working with strong acids. Take the negative log of that number, and that will give you the pH. All right, so a lot of stuff to work on. Even though it's the same formulas really again and again and again, you got a couple different applications to practice with. So as always, definitely go through, try out those practice problems, make sure you're comfortable with calculating pH. I hope you found this video helpful. Thank you for tuning in.